Hello, my name is Victoria, and today I'm going to be talking about our paper on the impacts of differentially private synthetic data on downstream classification fairness. Our primary motivation for this work was to investigate the intersection of the impacts on fairness, privacy, and utility when differential privacy is used in machine learning algorithms. Machine learning models are used in high-stakes settings on sensitive data in domains such as medicine and consumer finance, but these models can have disparate performance on minoritized subgroups. For example, previous work has shown that commercial face classification algorithms have higher error rates for darker-skinned individuals. These impacts can amplify existing prejudices against minoritized groups while maintaining the guise of numerical or automated impartiality. This disparate impact can occur for a number of reasons, for example, class imbalance in the underlying training dataset. As shown here, the popular Celeb AHQ facial recognition dataset is skewed towards lighter-skinned individuals and females. In such cases, when it's difficult to gather more minority data samples, synthetic data augmentation is often suggested as a solution to bolster the minority group's data presence. Synthetically balanced datasets created by neural networks such as generative adversarial networks or GANs can augment training datasets. This has demonstrated some benefits for reducing disparate subgroup impact. However, GANs and the synthetic data generated from them are vulnerable to privacy attacks that can expose sensitive information about individuals in the underlying training data. Differential privacy, or DP, is the leading technique for preserving privacy in statistical and machine learning settings. DP guarantees privacy by ensuring that the inclusion or exclusion of any particular individual does not significantly change the output distribution of an algorithm. Training GANs with DP has been shown to generate useful synthetic images on simple data sets such as MNIST. However, to our knowledge, there haven't been any investigations into the effect of DP synthetic images on the intersection of utility, privacy, and fairness in downstream classification models. Much of past DP-GAN research has also not taken advantage of state-of-the-art architectures such as progressively growing GANs, or PG-GANs, that have been shown to be extremely useful at generating higher dimensional image data. In our work, we investigate the viability of using DP synthetic data for improving both utility and fairness of downstream classification models while maintaining privacy. We analyze the trade-offs between utility, privacy, and fairness in the use of DP-PG GANs for synthetic training dataset augmentation in downstream classification tasks. To date, work with DP-PG GANs has naively applied the Renier differential privacy accountant, or RDP accountant, to track the privacy level of the model. The RDP accountant assumes a constant batch size and therefore underestimates the privacy loss in PG GANs, where the batch size actually decreases as the model grows. I'll provide an overview here of our proof to extend the RDP accountant for varying batch sizes. Additional derivation details and extensions of this proof can be found in our paper. Using the RDP composition theorem and type bounds on the RDP sampled Gaussian mechanism, or RDP-SGM, let the composition of T homogeneous alpha epsilon RDP-SGMs with a constant sampling probability Q result in an alpha epsilon prime RDP mechanism that meets the inequality displayed here. We can extend this to the case of decreasing sampling probability for progressively growing GANs. We start by again taking T RDP SGMs. This set of mechanisms is partitioned k times. For each partition, the original sampling probability decays. This means that the upper bound of the composition of this set of heterogeneous mechanisms will result in the inequality shown here. We use this inequality to calculate the privacy bounds of RDP-PG GANs. Now I'll go over our experimental pipeline. We first train our progressively growing GAN models. On each of our datasets, we train GANs at 4 different levels of privacy: none, low, medium, and high. We then evaluate the quality of the images generated from these trained GAN models using Fréchet inception distance, or FID. We also perform membership inference attacks on the GANs to evaluate their robustness to privacy attacks. We then use the trained PG-GAN models to generate balanced synthetic datasets. These synthetic datasets are used in our downstream model training, where we train logistic regression, random forest, and multi-layer perceptual models on the synthetic datasets. We then evaluate the model performance on the real test datasets and examine the standard group fairness metrics of performance, parity, recall, and specificity gaps in each setting. Finally, we perform an evaluation to determine how much influence each subgroup has on the downstream model's predictions under different privacy settings. We ran this pipeline for a total of 5 datasets: 2 chest X-ray datasets, Mimic CXR and CXP, 2 facial datasets, Celeb AHQ and Fairface, and 1 dermatology dataset, ISIC. The skin tone labels for the facial and dermatology datasets have been automatically generated using the Fitzpatrick dermatology classifications. Each dataset has a label for protected subgroup identity, as well as a target label for classification. The GAN models are trained on a combination of these 2 labels, while the classification models predict only the target label. In the chest X-ray and facial attribute domains, we have 2 datasets, which allows us to examine cross-dataset generalization. We would like to note here that there have been several facial datasets that have been created recently by the computer vision community, such as Celeb AHQ and Fairface. The collection and use of these datasets has led to concerning and unethical research due to the inherent systemic biases, such as sexism, racism, colorism, and ageism from the collection of these images and their labels. Our analysis serves to demonstrate the negative effects of using these labels. We do not condone the use of and prediction on these datasets in practical scenarios, and we emphasize to everyone here that the irresponsible and unethical usage of these labels and datasets could have harmful impacts on the research community and on society at large. I will now go over the results of each of the evaluations I mentioned in the pipeline previously. First, let's take a look at the quality of the images generated from the GANs. We found that the models trained with DP showed significant FID improvements when using progressively growing training. This demonstrates that the FID gains experienced by the large, high-quality image models from previous work are extensible to models trained with DP as well. It also demonstrates the need for our formulated privacy accountant that I covered earlier in order to accurately support privacy tracking in progressively growing learning. When evaluating the effect of increasing privacy levels on image quality, we found that higher privacy levels result in lower image quality across all datasets. An FID score of closer to 0 means that the generated image distribution more closely resembles the training image distribution. We show quantitatively here that FID score increases as the privacy level increases. Qualitatively, in the images to the left, we see that the images get more pixelated and more noisy as privacy increases. However, we found no significant trends in the FID difference across the protected subgroups across the different privacy levels. Next, we looked at the susceptibility of our GANs to privacy attacks. We used white box membership inference attacks in our evaluations. The attack is successful if it is able to accurately predict which data points are from the original training set of the model. In a white box attack, the adversary attempts to infer whether a particular image belonged to the original training set of a generative model based on that model's ability to reconstruct that image. We evaluated whether increased privacy reduces attack success in 2 settings. First, in the setting where the training and test set of images are from the same distribution or within the same data set, for example, when they are both from Fairface, as well as in the setting where the training and test set are from different data sets in the same domain, for example, across Fairface and Celeb AHQ. Here we show the AUC of the white box attacks, where a higher AUC means that the attacker can more accurately infer if an individual's data was used to train the GAN. Prior work demonstrates that membership inference is unsuccessful in GANs that are trained on large enough datasets. We observe this to be true across all privacy levels when the training and test sets are from the same dataset. However, when the training and test sets are from different data sets, non-DP GANs are vulnerable to membership inference attacks. In this setting of dataset shift, DP protects GANs from privacy attacks. We also found that increasing privacy levels results in less protection for the minoritized subgroup of dark skin tone in the presence of dataset shift for the Celeb AHQ dataset, the most imbalanced dataset used in our evaluations. This trend was not observed to be present amongst the other, more balanced datasets. We can visualize the results of the white box reconstruction attack here. We can see that the non-DP models can reproduce the training set images almost exactly. In real life, dataset shift is a common occurrence, so differential privacy is essential for preventing these attacks, especially when a model is publicly released. Our next evaluation after training the classification models on the balanced synthetic datasets is to evaluate the performance and fairness of these models. We found that the AUC of the classification models decrease as the privacy levels increase across all datasets. This means that the reduced image quality from the DP models results in poorer downstream model performance. However, we don't observe any trends in any of the group fairness metrics as privacy increases. In addition to standard group fairness metrics on downstream models, we also measure fairness in terms of the influence of each synthetic training data point. For each generated dataset, we use Cook's distance to evaluate the influence of each training point on a downstream regression model. Cook's distance quantifies the effect that the training point has on the downstream model's predictions based on the change in the model's prediction values when that point is excluded from the dataset. A highly influential point is considered to be any point that has a Cook's distance of greater than 4 over n, where n is the total number of training data points. We measure influence fairness as the percentage of highly influential points from the majority class. In other words, fair influence means that the set of highly influential points should contain equal proportions of the protected subclasses when we train on the balanced synthetic datasets. We found that more influence tends to be given to points from the majority subgroup in imbalanced datasets as privacy level increases. In Celeb AHQ, the most imbalanced dataset that we use in our evaluation, this means that the majority lighter skin subgroup goes from being around 50% of the highly influential training points in the non-DP setting to around 76% of the influential data points in the presence of any DP. This removes almost all the gain in influence that the minority dark skin subgroup gained when we use the balanced synthetic dataset in the non-DP setting. The models trained on synthetic data created from other more balanced datasets used in our evaluations do not experience the same level of disparate impact or do not display any consistent trends. So, what else do these results all mean? Our results highlight that machine learning has a need for real, diverse data in our training datasets. Lack of diversity in training datasets is known to amplify societal bias for minoritized subgroups. Our analysis emphasizes that biased datasets may still have disparate impacts on downstream classification influence, even when the real dataset is not used directly in the downstream training, and even when the synthetic dataset used for the training is balanced. Therefore, supplementing or replacing datasets with synthetic data does not mitigate the fairness concerns caused by the existing biases in imbalanced datasets. It also means that there are significant privacy risks to using synthetic data. Synthetic data augmentation is often explored as a solution to missing data or to data privacy issues. Although synthetic data can appear realistic and promising to use as a replacement for real data, the privacy risk associated with doing so remains high. While commonly used for creating synthetic data, generative models do not guarantee privacy by design. We have shown that GANs trained without DP are vulnerable to membership inference attacks, especially in the presence of dataset shift. Releasing a GAN model therefore exposes the training set to attackers and can result in the leakage of sensitive data. In summary, we have demonstrated that training with DP can address privacy concerns, but has the potential to skew the influence towards majority subgroups, exacerbating already existing inequalities in the data collection process. While DP has strong theoretical guarantees, it can significantly degrade model utility when applied in real-world settings. The loss in utility of the synthetic data as privacy increases causes much higher rates of misclassifications in downstream models. This decrease in model performance can lead to disastrous effects in important settings, such as weapons identification and pedestrian identification for autonomous cars. Our evaluation also does have some limitations. Again, we want to caution that the automatic detection of facial labels is only performed as an example and should not be considered a valid task for deployed applications. The analysis we present also contains limitations in the automated skin tone categorization, since skin tone categories are known to be subject to lighting conditions and are inherently subjective even to human dermatologists. Cameras are also known to less accurately capture darker skin tones. Therefore, more objective data sets and labels should be pursued for future evaluations. In conclusion, we've shown that more work needs to be done on differentially private data synthesis before it's ready to be applied in real-world settings, such as high-dimensional medical images. Additional future work can also be done around the training of progressively growing models with differential privacy. When training at low resolutions with DPSGD, the noise added during the training process prevents the model from effectively learning essential low-level structures of the images, resulting in much worse quality images than if the noise is only added when the model is learning the high-level details. Theoretical work must be done around how this technique would affect privacy guarantees. Thanks for listening to our presentation. I would like to thank everyone who participated in making this work happen, especially the computing resources that were provided by the Province of Ontario, the Government of Canada, and the companies sponsoring the Vector Institute. These are several of the works that I mentioned during this presentation. You can find a full list of our citations in our paper. Please feel free to reach out if you have any questions regarding this work. Thank you for listening.